Most books explain that when you make ion configurations, they're going to have a special rule for how they're filled. Now, that's a good thing to remember, is that there's a very specific thing you have to remember to do, and that you want to be very careful when you're working with setting up electron configurations for ions. But I don't really want us to learn that it's a special rule. We're following the exact same rules that we always have when we're thinking about the physical interaction between positive charges in our nucleus and the tiny little fast-moving electrons that are floating around way outside of them. Now, if you remember that in our model, we can picture the nucleus as being about the size of a marble inside of a football field, and in that football arena, you've got electrons that are the size of fruit flies or maybe smaller, zipping around at close to the speed of light. If you're thinking of it like that, remember that there's nothing that's going to be changing in our nucleus. The only thing that's going to change is how many electrons are sticking there. So, if another atom were to come along and steal an electron, it's going to steal the farthest out electrons. If you were to get more electrons, they're just going to have to stack in using our filling rules. And that's what we're going to see as how we handle electron configurations for atoms. Now let's see one in practice, because we can make the distinction make a little more sense. So it's asking us here, what's the correct extended and condensed notation for iron 3? Before we do those notations, let's see how we fill them using the boxes. Now, first thing to do, we need to know how many protons are on iron. Don't immediately think of electrons. Think about protons first. So let's take a look at the periodic table. Now here we see that we have iron at atomic number 26. So we're going to have 26 protons to work with. Let's just jot that down. 26 protons. Now, how many electrons are we going to have to work with? Eventually, we're going to have 23 electrons. But remember, nature didn't make the ion first. Nature made the atom first. You start out with that nice neutral atom. Then you start having the electrons being stolen or extra electrons being donated. But the first thing that was stable was the atom itself. So we're going to approach it the same way. We're going to build our atom first, and then we're going to make any changes that are necessary. So I'm going to fill in 26 electrons, and then I'll steal 3 electrons away in order to turn it into the iron 3 ion, just like nature would have done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's mix it up a little bit. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Notice a moment ago I flipped some of these around. That's just because I want to remind us that it is a random process, but we don't bother drawing it that way usually. So we had 20 electrons a moment ago. Now I get my last 6 electrons in. 21, 22, 23, 24, 25, 26. Notice this is a great one to test Hund's rule and make sure that you're actually doing all of your electron filling rules correctly. If you're doing them wrong, you would have filled the second one right here and a second one right here and left these 2 empty. And so I would know immediately that you weren't following your rules the right way. So that's a nice little test question that I can do. Now you can see that we've got 6 electrons here. We're going to steal away our 3 electrons that we need in order to turn into the iron 3+ ion. But I'm going to appeal to the Bugs Bunny visualization of what's going on here. Now what happens when Bugs Bunny's walking past Elmer Fudd's house and he smells the delicious pies that he's cooked? Well, one is cooling on the windowsill, one is sitting inside the kitchen on the table. Which one does Bugs steal? He doesn't go inside the kitchen to take a pie, he takes the one sitting on the windowsill. Yes, that's ridiculous for an analogy, but it's also very accurate. The same thing is true here. So as I bring another atom nearby to start stealing electrons away, making the 3+ charge, where are they going to grab the electrons from? The farthest out portion of the atom. It's not about energy, it's about location. Location, location, location. And notice that the 3D orbital is still going to be in n equals 3. Its radius is going to be in the 3s. Not in terms of units, just in terms of orbit. However, this one is sticking further out, the 4s orbital. So the first 2 electrons that it's going to steal are going to be the 2 that you see right here. We're going to steal 1 and 2. Get rid of these as well. So we've stolen away 2 electrons. We still have to steal 1 more electron away. Now the 3D is going to be the farthest one out. Where are we going to steal the electron from now? Think of my dorm room analogy. If I have 5 rooms on a floor, one has 2 people in it, all of the others are singly occupied, and one person must move out. If this guy moves out, these 2 people are feeling pretty jealous because they're the only people who still have roommates. However, things end up being pretty good if you have that one be the person who moves out. Now everyone ends up having their own room. All of your electrons are now going to be pretty stable because you've minimized the amount of repulsions. You don't have 2 negative charges in the same region of space anymore. So this will be the spot where you steal your 3rd electron. This is going to be our electron configuration for the iron 3 ion. So now we're going to come back to our original question. What is the correct extended and condensed notations for iron 3+? Now we could answer that fairly quickly by just converting this into our condensed notations and our extended notations, but let's do it from scratch. So I'll do it from scratch over here without looking over at the box diagrams. If you want to follow along looking both places, that's fine, and that'll allow you to get a feel for how these things are working. But I'm not going to be looking at this at all. What I'm going to do is I'm going to completely use my filling rules. So I start out with my 1s. My 1s electron orbital can hold a total of 2 electrons. My next orbital will be the 2s, which can also hold 2 electrons. I'm up to 4 total. I then get to my 2p. 2p can hold a total of 6 electrons. I'm now up to 10 electrons. Keep going. My 3s can hold 2. So I'm at 12. My 3p can hold another 6. I'm at 18. So I'm not up to 26 yet, but I'm getting pretty close. Now I'm going to do my 4s, which can hold 2 electrons. I'm now at 20 electrons. To get to 26, I have 6 more to place. They're going to go into a 3D orbital, which can hold up to 10. I only have 6 remaining, so I've filled up my entire atom with my 26 electrons. For my neutral iron atom. Now that I have a neutral iron atom, I'm ready to go to make it into the 3+. Now, just like we described over on this side, we're going to take it from our highest radii. Highest radius will be the 4s that I have here, so I'll use up 2 of the electrons right there. I'm now at a +2. In order to make it a +3, I have to steal my next highest, so I'll be at 3d5. So that's my extended notation. For my condensed notation, I can then think through what I had as my complete condensed notation a moment ago before I stole any electrons. Remember, I still had my 4s2. I'll go ahead and I'll do that in a different color to remind myself that they're not there anymore. So these are the ghost electrons that I've removed, my 4s2, and I had 1 more that I had removed right here. We never write them. I just want us to be able to see something about it. Now, notice that if I'm trying to make my condensed notation, what I need to do is I need to spot where my dividing line was for when it looked like a noble gas. All of these things on the inside look like a noble gas. I filled up my s's and my p's. I started a whole new row. Notice when we go from a previous number's p to the higher number's s, that's when we're going to be starting a new line on our periodic table. So let's take a look at what our noble gas configuration will be. So you can see over here, argon is going to be the previous noble gas before we come all the way around to iron. So let's go ahead and use argon as our starting point. So I'll go ahead and write argon in brackets. All of this is argon-like. All that I have over top of my original argon is going to be my 3d5. So that's going to be my condensed notation for iron 3+. That's how we can do our electron configuration for ions. Notice that this terminology over here, this notation, and all this notation, you already knew how to do that. The only new thing that we've added is how we correctly steal electrons from this. Now, I also mentioned earlier that we can have something different happen when we're adding electrons. So let me go ahead and just put things back to where we started. this is back to having a neutral atom of iron. Now suppose for some reason, and we'll see later on that this would not be something that's terribly stable. Suppose somehow, with really high energies involved, we made an iron 2- ion. So what's going to be our rule there? Remember, we have all of our low energies filled. We aren't stealing anything, so it's not a matter of grabbing something far away. If it does go into a higher orbital, it's just going to immediately fall down to the lower energies if it can. And so we just keep filling our normal way. So for this one, we would just add 2 more electrons. That's why I really want to emphasize, when any of your books tell you that there's a different rule for your negative ions and a different rule for your positive ions, your anions and your cations, I don't think that's the case at all. We're just following the exact same rules we've always followed. Fill by energy, steal by radius. And that's how you can make your ion electron configurations.